All right, so first of all, so we were talking about some other type of algorithms for computing eigenvalues or for diagonalizing a symmetric matrix. And this Jacobi method was sort of picking an off-diagonal term and trying to make that one zero over and over again. And but before that, we talked about QR iteration with shifts. And there was a question about the Wilkinson method of looking at the eigenvalue of the lower bottom left, bottom right block and picking an eigenvalue closest to A and N. And the question was, what if there's symmetry involved and somehow you need to break a tie? And I guess the strategy is to just pick one randomly. If you have two eigenvalues that are closest to A and N, just pick one of them. That makes sense?
Yeah.
All right. What other methods are there? There's something called bisection. Okay, so let's assume again that you have a symmetric matrix and so that eigenvalues are real. Let's also assume that we've put it in tridiagonal form. And like that. And then let's call the leading principal submatrices call them A1. So A1 is going to be A1. A2 is going to be A1, B1, 2, A3, etc. up to AN. Does that make sense?
Mm-hmm.
So that should be N by N. All right, so this is the leading, so sort of like we did when we talked about LU decomposition, we were looking at the leading principal submatrices and asking that they were all non-singular, right? Well, now a typical assumption here at this point that we can add is that all of the off-diagonal terms are non-zero. Because if one of them is zero, then you can kind of, you know, if one of them is zero, then you can divide it into two blocks and kind of treat them separately. All right, so let's assume that. Now, note, this implies that all of the eigenvalues are distinct. Um, why is that? Well, let's think about it for a second. So if you look at this A minus lambda I, it's going to look like this. Right? And how do you show that lambda, for instance, is not doesn't have multiplicity? Well, you could go ahead and solve the homogeneous system with this matrix and check the dimension of the kernel, right? The dimension of the solution set. So how do you do that? Well, you could, for instance, do Gaussian elimination. And so when you're presented with this and you're trying to do the reduced rational form, and you know that B1 is not zero, right? You don't really know much about A1 minus lambda, but you do know that B1 is non-zero by hypothesis. So the first thing you might do is switch, right? So you would swap 2 and 1, right? So then it would go B1, A2, actually 0 after that. And then, right? And then B2. So. Agree with that? As the first step in the reduced rational form. Right. And so if you divide by B1 and you make this 1, then you can actually make this one 0, whatever it is. And you will definitely get a pivot here. Right? Okay, but then you can repeat, right? Once you've done that, now you look at this block, and when you make this 0, you don't really perturb the third line. So again, you're going to be able to swap these two lines, and then B2 will be non-zero, and you'll definitely get a pivot there, right? So by induction, we get at least as many pivots as there are off-diagonal terms, and there's n minus 1, so we get at least n minus 1 pivots. Okay, that makes sense? Right, so that means that we get at most 1 degree of freedom, and so that means that all of the eigenvalues are simple. So in particular, you take one of those leading submatrices, principal submatrices, they also are going to have distinct eigenvalue. and you can order them. Like that. But more interestingly, there's something called Cauchy interlacing, which I think you did in the homework, was question 5.4. This tells you that the eigenvalues of the k leading submatrices kind of interlace with the eigenvalues of the next one, right? So lambda j k plus 1 they will fall like that. Let me give you an example. Is this good so far? Does this ring a bell? Question 5.4.
Yeah.
That makes sense. I think I missed the connection though as to how we arrived that they were distinct eigenvalues. We had 1 degree of freedom that implied something.
All right, the 1 degree of freedom means that the corresponding eigenspace, right? The eigenspace for lambda is the set of solutions to the homogeneous equation a minus lambda I x equals 0, right? So if the reduced rational form of a minus lambda I has at most 1 free variable, that means that the dimension of the eigenspace is at most 1. And that means that there can be 2 eigenvectors, linearly independent eigenvectors sharing the same eigenvalue.
Okay.
Right. All right. So, okay. So we have the Cauchy interlacing. Let's do an example on an actual matrix. Let's take 1, 1, 2, 1, 2, 1. 4x4 matrix. And you may actually check, there's a nice recurrence in this where the determinant of AK can be computed from the previous ones. You might actually try to do that to prove this. It's just the, I think it's called a class expansion of the determinant. You know this fact? If you want to compute the determinant, you can pick a row and a column. So, well, you can pick a row or a column. Let's say pick the last row, and you look at one term, and you cancel the row and column corresponding to that one term. You multiply by the determinant of the rest, and then you take the next term and you do the same thing. And there's some signs that need to be decided, but there's a rule for that. Do you know this fact?
Mhm.
Is it called Laplace extension? I never remember.
I think it has wording like that, and then that linear algebra textbook refers to it as that, as well as like cofactor expansion.
In fact,
I think it's another name.
Yeah, that's what I know it as.
okay, so it's not hard to believe that because of the tridiagonal structure, you get this nice recurrence. And so let's look at, so for instance, in this case, the determinant of A1, well, that's just 1. And then the determinant of A2, okay, so that would be these 2 by 2 block, that's -1. And then the determinant of A3, I can either do it, wouldn't be too hard to do it, because you get 0, 0, 0, -2, -1. So that's going to be -3. Maybe I'll use the recurrence for the 4th one. Okay, so I need to take AK, which is -1, times the previous determinant, which is 3, minus bk -1 squared, that's 1 squared, and the determinant of A2, which is -1, so +1. All right, so you get this sequence of determinants, and this sequence of determinants actually has a name. It's called Sturm sequence. So actually it starts with 1. And up to n. And now you do the following. You use this sequence to do the following. Okay, so the first one is 1. So here is 0. Here's 1. And the next, so A2 is negative, right? -1. So it means, remember, the determinant is the product of the eigenvalues, right? So if it's negative and there's 2 eigenvalues, well, one has to be negative, the other has to be positive. So that means that one is over here, and the other one is not just positive, but over there because of the interlacing. Right? So this is A1, this is A2. That makes sense? Okay, the next one is negative. Maybe you tell me, where should I put the next 3 eigenvalues?
One negative and then 2 being positive, and then one outside of the 2 points and then 1 in the middle.
Yeah, so 1 outside. That, right? And then the next one that goes in the middle, though, has to be positive. Right? Because of this interlacing. All right, and then the last one is positive. So that means there's two that we need to put here because of the interlacing. But the other two, well, one is going to be positive because it's going to be between these two, so it's going to be somewhere here. It shouldn't actually be in the same spot. Well, I don't know, maybe. But then the last one, because the determinant is positive, better be over on the negative side, right? That makes sense.
Mhm.
All right. So it's a fact because of this that the number of negative eigenvalues equals the number of sign changes in the storm sequence. Okay, so here let's see what you start at 1 and then you change sign here and then you change sign again. So there's two changes and there's two negative eigenvalues. Okay, so this is a theorem that needs to be proven by induction or something. And it's the observation that makes the thing work. So, for instance, let's say you want to find the number of eigenvalues in some interval with a other than 0. Well, you just shift to find the number of eigenvalues to the left of a, shift a, and then that actually so let's say you want to find the eigenvalue in some half open interval AB. Basically you do two shifts. You do the number in minus infinity B minus the number in minus infinity A. And so you can kind of zero in on eigenvalues by, for instance, do a bisection algorithm where you figure out how many there are in this interval, you split it in half, and then you check. Right? So eventually, let's say that there's 1 here. You figure out there's 0 here and 1 there, so then you split this one in half. There's 0 here and 1 there, then you split this one in half, then there's 0 in, the bisection method will kind of zero in geometrically into an eigenvalue. That makes sense.
Yeah, that's cool. That's kind of interesting and clever. I mean, we always all like to apply a binary search, right?
Yeah.
Whenever we do anything.
Oh, yeah, it's called binary search. Yeah. And also it can be parallelized, this one.
Mm-hmm.
All right, so this is very different in a sense. It's dealing with the, with the determinant, with finding the roots of the characteristic polynomial. But and using the structure, this interlacing property. Very different from the other ones. And then maybe the last one I will mention. Well, in this vein, it's called divide and conquer. All right, so again, let's assume a metric tridiagonal and non-zero off diagonal terms. So fix K. You can always write A as follows. So think of A and give it a block structure. So give it a block structure. There's a block there. Here, A1 is going to be the K by K block. Okay. And then the rest, well, that's going to be A2. And because of the structure, the tridiagonal structure, these blocks, they look like this. There's a beta in a corner, right?
Mm-hmm.
All right, so the idea is to rewrite this as a sum of a modified block A1 hat, A2 hat, plus something that looks like this. All right, so that's certainly doable. Basically, all you have to do is subtract beta from the lower entry here, the bottom right entry of A1, and you get A1 hat. And also subtract beta from the top left entry of A2 to get A2 hat. All right? But the advantage now is that this is a 2x2 matrix, block diagonal. And this term has the advantage of being rank 1. Because the two rows are the same. Okay, so with that, let's assume that K, let's pick K to be roughly, n over 2, to have blocks of the same size. And also assume that the eigenvalues of A1 and A2 are known. Okay, so it's a way of iterating. So that makes sense. We assume that the eigenvalues are, we've already solved the subproblem here and here, because A1 hat and A2 hat have the same exact form as A. They're going to be tridiagonal, and they're going to have non-zero diagonal terms. They're going to be symmetric and all of that, right? So let's assume that we've already solved these two subproblems, and see if we can then solve the overarching problem. All right, so let's assume that they are known. So that means that, for instance, we can diagonalize A1 hat, U1, D1, U1 transpose, and A2 hat, U2, D2. Yeah, I claim that then I can rewrite A as U1, Q2, and then B1, B2, plus some term here, Q1 transpose Q2 transpose. And the question is, what is the term I need to put there to make everything work? And it's going to be beta ZZ transpose. ZZ transpose is an outer product. It's the rank 1 matrix. And I need to tell you what Z is. Beta is the beta oh, what happened? Oh, sorry. Beta is this beta here, right? This off-diagonal term of the K by K block. That makes sense?
Yeah.
Yep.
So it's actually BK. But, all right, so what is Z? What is Z that makes everything work? Well, I have to tell you what Q and Q2 are. So it's a bit strange, but I'm gonna think of Q1 in terms of its rows. And it's a K by K, so that's gonna be like that. And Q2 in terms of its rows, and that's going to have n minus k rows. All right. Then the claim is that Z is simply the concatenation of the last row UK, but as a column, and then the first row of Q2 as a column. Write it like that. And Z transpose then is going to be UK transpose V1 transpose. So when you take ZZ transpose, that's an adder product, so it's going to have kind of a block structure where you take UK transpose, V1 transpose, and then UK V1 transpose, and V1 UK. That makes sense?
Mhm.
All right, so when you do, when you unfold here, you know, you multiply from the right by this and from the left by that, then you're gonna get when you do ZZ transpose Q1, Q2. So, all right, so then what does that mean? The beta will, you know, the beta is just a scalar that'll come out. This remember, when you take a diagonal matrix and you multiply by a diagonal matrix from the left, you multiply the rows, right? So you're gonna get UK transpose, V1 VK transpose, and UK. So this multiplies the row, so Q1 plus R2. And then from the right, you multiply the column, so Q1 transpose. Right? Makes sense?
Mhm.
All right, but let's think about it. So what is Q1 times UK? Well, the U's are orthonormal. So you're gonna get 0, 0, 0, 0, 0, 1, right? That's gonna be EK, basically. And then the same when you take the trench, so EK, EK trench. Right, and likewise here, when you take Q2 times V1, you're gonna get 1, 0, 0, 0. So you get E1, E1. And then, you know, by the same token, when you here, you're gonna get zeros. Sorry, you get zeros? No, you're gonna get. Okay, so here you're gonna get. Okay, but check for a second here. V1, V2. Yeah. This is going to be EK E1 transpose. This is going to be E1 EK transpose. The problem is that EK is in R K, and E1 is in R n minus K. Yeah. But that's fine because you can always take these type of products because, so this guy is going to be K by 1, and this guy is going to be n minus K by 1. When you transpose it, the inner dimension is 1. You can always do that. You need to check that you get exactly, this matrix, which is 0 everywhere, but it's got 1s. In this corner. That's terrible, sorry. That makes sense?
Yeah.
So then with the beta, you get exactly, you get back what you wanted. This matrix here, this rank 1 matrix. All right, so that's that. You can write it like this. So in a sense, you can use this change of think about it in terms of a change of variable. And then A becomes diagonal plus a rank 1 perturbation in that coordinate system. Another question is, how do you find the eigenvalues of a rank 1 perturbation of a diagonal? Right, so it's kind of in general. So problem, find the eigenvalues of D plus a rank 1 perturbation, W. And let's assume, because the BJs are non-zero, so where D has some diagonal entries and the DJs are distinct. All right. So that's just kind of the general problem. So first of all, assume that all of the entries of W are non-zero. Because otherwise you can reduce, right? Otherwise. In the outer product, if Wj is 0, you're gonna get zeros, in both the row J and the column J. Remember, the entries of the outer product, I and J, are Wi times W. That makes sense?
Yep.
Okay. So we assume all of the Wj's are non-zero. And let's suppose that we have an eigenvalue. So WW transpose U is lambda U or some non-zero vector U. All right, let me rewrite this. I'm going to write it as d minus lambda I u. I'm moving the lambda u to the other side. And then I'm going to have this other term, w transpose u. Well, but that's just a scalar multiple of w. And then I can, assuming that p minus lambda I is invertible, I can multiply by the inverse. That. And then at this point, I can also multiply by W transpose. Right. And now you see I can factor out the dot product. Times 1 plus this quadratic form equals 0. That makes sense?
Yeah.
Just a little bit of algebra. Okay, but now we have a product of two things equals 0, right? So let's see, if W transpose U is 0, what does that mean? Well, if you go back up to the top, it tells you that du is lambda u, right? I star here. Agree with that?
Yes.
Yeah, okay, but D is diagonal. So u is ej to some j. It's a standard basis vector, right? But then W transpose ej is wj, which is not 0 by hypothesis, so we get a contradiction. All right, so that can be. W transpose u is not 0. And so that the other term has to be 0. So 1 plus. And now think about what is d minus lambda I inverse? What is this quadratic form? Coordinates, the quadratic form says that wj squared over dj minus lambda is 0. Okay. So this is a function of lambda set equal to 0, and it's got a name. It's called the secular equation. You can try to graph it. It's the sum of a bunch of, it's like a rational function. Right? It's 1 over lambda shifted. So it's going to look like something like this. Some asymptotes. All right. The asymptotes are the values of D1, D2, 3, etc. right? Because that's when lambda equal dj, this blows up. And the solutions to this equation are these roots. Okay, so that's a nonlinear problem, but there are methods for finding those roots. So for instance, you can use Newton's method. And it can be quite fast, right? So you start with an initial guess. You go to the function, you compute the tangent, and that gives you the second guess. You go to the function, you compute the tangent, you know, you're gonna go really fast towards the root if you do that. Okay, so that's the idea of the divide and conquer method. I think I'm over time now. That makes sense?
Yeah, that was it's interesting. It was a fun journey through it. I think it seems more involved than, say, these iteration approaches that we had looked at prior. So I guess you can kind of get an idea of why QR iteration is very commonly implemented. But
yeah, I think this is more recent, this divide and conquer, and can be quite fast actually.
okay.
Yeah, again, because you split, right? So every time you split.
Sure, you can just dump it out there in some infrastructure and
so
have that in.
It can be quite fast actually.
And this entire semester, I really enjoy all the block matrixy arguments. I don't know, they seem like a very intuitive, and it's always an interesting little puzzle. That's not too bad. And it always gets us somewhere.
Yeah, I know. It's like, how many ways can you dissect something? Incredible.